alternating current. So Kate builds a circuit with a signal generator. So that's like an AC power supply where, oh my goodness, the frequency can be adjusted. It's initially set to, stop that, a frequency of 200 hertz. And it has a a lamp with some resistance, 15 ohms, and a capacitor with a capacitance of 1.2 microfarads. They are connected in series. Show that the capacitive reactance is 663 ohms, and hence determine the impedance of the circuit. So we need to find XC, and then we need to find impedance. So, looking at our formula sheet, where are we looking? We are looking in, I'm so blind. Oh, yeah. Bottom two rows are the AC circuit equations. So on the right hand side, we see XC, the capacitive reactance, is 1 over omega C. And you see the bottom left, the inductive reactance, XL, is omega L. So, for the capacitive reactance, XC, 1 over omega C, and omega is 2 pi F. Yep. So we can express that as 1 over 2 pi F times capacitance. Great. All we need to do now is substitute in our values. So 1 over 2 pi times the frequency, 200 hertz, times the capacitance. Notice it is in microfarads, so we need to convert that to farads. So micro means times 10 to the negative 6. So 1.20 times 10 to the negative 6. And computing that, check on my notes, we get exactly what they asked for. 663 ohms. Cool. Now that we have the reactance of the capacitor, we can find the total impedance. Where are we given that equation? No. The total impedance depends on both the resistance and the reactance. But unlike a DC circuit for resistors where you just add the resistances, we need to do a vector sum, right? So we have a right angle triangle, and to find the impedance, it is the hypotenuse. Right, so we have something like so. Z is impedance, this is the resistive part, and this is the reactive capacitance. So Z is equal to the resistance squared plus the capacitive reactance squared, all square root, which is 15 squared plus 663 squared square root, giving us an impedance of, that's pretty much still 663, right? Because 663 is so much larger than 15, the hypotenuse is pretty close to 663 when it's rounded. So I might do approximately equals. Cool. All right, and that is a merit question. Right, achieved if you worked out the reactance, and then merit if you link that to the impedance through the resistance. Even though the impedance is about equal to the reactance, we still need to show our working. All right, and now Kate, getting a bit bored, she changes the frequency from 200 hertz up to 20,000 hertz, and then to 200,000 hertz. And this will change the reactance of the capacitor, right? Notice it depends on the frequency. So give an in-depth explanation, what Kate will observe. And we need to discuss the impedance of the circuit, the current, or RMS current, and the brightness, right, which depends on current and voltage. And so if Kate keeps voltage constant, right, she's just changing the frequency. As impedance changes by Ohm's law, right, if voltage is constant, if impedance goes up, current would go down. If impedance goes down, current would go up. Right, and then this links on to the power, right, the brightness of the lamp. So we need to explain this, but in terms of starting with the frequency. So frequency into reactance, into impedance, into current, and then into power. Oh, my laundry's getting wet. I'll be right back. Okay, we're back. Laundry saved. Sorry about that. Alright, let's answer this one. So where to start? You could show calculations. So for 20,000 hertz and 200,000 hertz, you could work out the impedance, well, reactance, impedance, current, and power. However, if we explain it in enough depth, that's what they're asking for, right? So I'm going to just explain, but I do encourage you to do the calculations. And if you just want to check your work, well, ask a friend. What am I saying? So let's begin. As frequency increases, so from 200 to 20,000, what's going to happen to reactance? If frequency increases, capacitance stays constant, reactance will decrease. So we'll say XC decreases. Now, how does that affect the impedance? Well, resistance is constant. So R is constant. XC decreased. So impedance will also decrease. Okay, how does this affect current? Well, voltage is constant from the power supply. Impedance decreased. So current will increase. And that's by Ohm's law. Okay, and how does this affect the brightness of the lamp? Again, voltage is constant. We just discovered or discussed current increased. So power will also increase. Now, how does this relate to brightness? Well, power and brightness are like proportional. So brightness also increases. I would say that's an in-depth explanation. Now we've discussed 200 hertz to 20,000 hertz, right? But then she increases it to 200,000. Well, the exact same logic applies, right? Frequency is still going to be increasing. So reactive capacitance decreases. So impedance decreases. Since voltage is constant, current will decrease, and so power will increase. Current will increase, and so power will also increase. However, for 200,000 hertz, the current, the reactance, let's just use symbols, XC will not change as much. If you're like, well, why is that the case? We just times frequency by 10 again. Well, looking at the equation for XC, it's an inverse function, right? 1 over F. And so the inverse function looks like this, right? It's part of a hyperbola. And so at the start, if you multiply like by a factor of 10, it's a large drop. But if you go 10 again, it's a smaller drop. And so this really, really high frequency isn't actually going to change the reactance much. And so impedance won't change much, or will not change as much, right, compared to the initial change. What does that mean? Current will not increase as much, and so brightness increase will be small, right? Not unnoticeable, but not as significant as the first jump in frequency. Cool. And you do need that second part for excellence, because it does ask an in-depth explanation as she went from 200 hertz to 20,000 and then to 200,000. And so that's actually where, if you calculated it, you would see that change, that smaller change, more obviously. Yeah. Whereas I saw it in this equation, because I'm familiar with an inverse function, so I just sketched it out, realized that, okay, if frequency is increasing as at higher values, the change in reactance won't be as much. And this is, of course, an excellence question. All right, on to part C. Okay, our Kate changes the circuit, makes it an RLC circuit. She adds an inductor with an inductance of 0.2 henries. And it is set at 2000 hertz. The lamp is off. Okay, but as she slowly decreases the frequency, the lamp suddenly glows brightly, but then it goes off at lower frequencies. Calculate the frequency at which the bulb glows brightest. Great, so if it's the brightest, that must mean current is a maximum, and current is a maximum when the frequency is equal to the resonant frequency, F0, which in your formula sheet is this one right here. Last column, fourth row. And in case you forgot, the resonant frequency is when the reactive inductance, or the inductive reactance equals the capacitive reactance. Right, so 2 pi FL equals 1 over 2 pi FC, and then you solve for F, and you get this expression here, this formula. 1 over 2 pi root of inductance times capacitance. And so substituting in our values, 1 over 2 pi square root. Inductance was 0.2. Capacitance was 1.2 times 10 to the negative 6. Right, from the previous question. Never draw my square roots long enough. There we go. And if you compute that, you should get 325 hertz. And that is, of course, an achieved question, right? It doesn't even say to explain what this means, it's just to calculate the resonant frequency. But they were sneaky in that they didn't say resonant frequency, so look out for things like when current is a maximum, when capacitive and inductive reactance are the same, when the lamp glows brightly, things like that. Alright, and part D, the last sub-question, explain how the inductor affects the impedance of the circuit, and why there is one frequency at which the impedance equals resistance. And it's at that impedance, right, of 15 ohms that causes the lamp to glow brightly. So this question is effectively asking you to explain resonance, but they've given a slightly different spin on it. So let's start by explaining how the inductor affects impedance. So XL equals 2 pi FL. So that's just on your formula sheet, bottom left, right? Instead of omega, it's 2 pi F. So the inductive reactance increases with frequency, right? They're proportional. Higher frequency, higher F means higher inductive reactance. Correct, so we've explained how an inductor affects impedance. Conversely, for a capacitor, if frequency increases, capacitive reactance decreases. Right, so higher F means lower XC, capacitive reactance. At the resonant frequency, which we worked out was 325 hertz, the reactive and inductive reactances are equal. Right? That is a definition of resonant frequency. What does this mean? Well, this means impedance is a minimum. And why is that? Since impedance is the resistance squared plus the difference between the reactances squared or square rooted, right? And if inductive and capacitive reactances are equal, that goes to 0. And we're left with just the resistance as the impedance. Another way of explaining that is you could use your impedance triangle. Right, we have resistance, we have XL and XC, and these are equal, which simplifies to just pure resistance. Okay, and now what does that mean if impedance is a minimum? So if impedance drops, voltage is constant, current will increase, causing the lamp, the lamp to glow brightly. Full stop. And so let's just reread the question. Explain how the inductor affects impedance. Done. Why there is one frequency at which impedance equals resistance, causing it to glow brightly. So we mentioned that frequency, and that occurs when the inductive and capacitive reactances are equal, and we showed the impedance equation, or the impedance triangle. So impedance was minimized, current will increase, so lamp glows brightly. Done. And that is, of course, an excellence question. Alright, I think you earned a break. I know I did. I'll speak to you later.